Hey guys, we're going to continue looking at our transformations. Today we're going to be looking at rotations. I do apologize, this video is going to be a little bit longer. There are quite a few examples towards the end of it. So if we're going through the examples and you think you've got a good grasp on it, feel free to exit out of the video and continue on with the practice that's on the website. So our goal here is that you can find the number and angle of rotations of different figures. Sorry, that was my cough. So rotational symmetry. So as we look at rotational symmetry, there's a couple key terms that we need to know. And I've also posted a little flyer of this on the website to help you out. So the number of rotations is just how many times can an image fit on itself as we rotate it. Okay. So we go through a 360-degree rotation, so it's all the way around. How many times will it land perfectly on itself? So here, right, we've got this little war club looking guy. The only way we can have it fit on itself is if we make one entire rotation. Our stop sign, or our stop symbol here, can make two perfect rotations. We'll see that in a second. The film reel is 3, and that flower is 4. And again, we'll see an example of this here in a second. Angle of rotation, you take the number of rotations, well, you take 360 degrees, because that's the whole rotation, and you divide that by the number of rotations. So for example, our little war club guy, the angle of rotation is 360 degrees. It needs to take 300, it needs to go all the way around before it can fall on itself. Our stop symbol, however, is 360 degrees divided by 2. So angle of rotation is 180 degrees. We have 180 degree symmetry. Our film canister thing here is 360 divided by 3, so that's 120 degrees. So that means every time you rotate it 120 degrees, it falls on itself. And then the flower over here is 360 divided by 4, that's 90 degrees. So every time you rotate it 90 degrees, it lands on itself. Okay. We also have these things called center of rotation. And it's a very specific spot on something that has rotational symmetry. Right? If the angle of rotation is 180 degrees or less, that means that if it has 2 rotations or more, it will have a center of rotation. If it has 360 degree rotation, so it doesn't have rotational symmetry, you can say that the center of rotation is anywhere. It doesn't really matter because it takes 360 full 360 degrees, a full rotation for it to come back on itself. So we've got the number of rotations that an object has, the number of times that it fits on itself. So like I previously said, so here we go. That war club, it's one full rotation. Okay. The angle of rotation is 360 degrees divided by 1. Again, so it's 360 degrees. A little stop symbol here. Right. There's 1, so it's flipped half the way through and then all the way back. So 2 rotations. 360 degrees divided by 2 is 180 degree rotational symmetry. Our film can, right? So 1, 2, and then back up to 3. So that's 360 degrees divided by 3 is 120 degrees. And then our flower here, right? We've got 1 rotation there, 2 or halfway through, 3, and 4. And the only reason why I've got the little dot here in the corner is to help show where our starting point is. Okay. So 360 degrees divided by 90 is going to equal, or sorry, 360 degrees divided by 4 is going to equal 90 degrees. So for every 90 degrees that flower is rotated, it's going to be, it's going to fall on itself. It's going to have rotational symmetry. So as we look at our star here within the pentagon, right, we need to figure out how many rotations it's going to take. So as we flip it, there's 1. We've got a little pink image in the back, so when it's hidden 2, 3, 4, and then we come back to start again, we have that dot to help us figure out where the starting point was. So 360 degrees divided by 5, we have 72 degrees of angle of rotation. So every 72 degrees that this shape is rotated gives us the same image. have our star within a circle. So something I want you to be thinking about, the pentagon with the star inside, it was a five-pointed star. It was a five-sided object, right? And we had five rotations. This is a six-pointed star, and it's considered a perfect star, so all of the sides are the same. We have six rotations. Yeah. So be thinking about things like that when you're looking, right? So if you've got a perfect image, you can kind of guess. So we have an equilateral triangle. That means that all the sides have the same length and all of the interior angles are the same, right? This doesn't work for all triangles. So a perfect triangle here. So we've got 1, 2, 3 rotations. Okay, so 360 degrees divided by 3 is 120. This is an example of what I was talking about. An isosceles triangle where two sides are long, one side is short. We have two congruent interior angles. It's down here at the bottom, right? So we've got this angle here and this angle here are the same. We only have one rotation, right? So it has to be a perfect thing where all the sides are the same. We've got 1, 2, 3, 4 sides that are the same. Flip it and rotate it. I'm sorry, not flip it. We have 1, 2, 3, 4 rotations that we can make. So 360 degrees divided by 4. Again, we've got a pentagon. I'm going to blaze through that one because, again, we just saw that. We saw that with the star on the inside, and the outside shape didn't change. We've got a regular hexagon. A hexagon has 6 sides. Again, I'm kind of moving a little quickly because I feel like we've kind of covered this material at this point, right? At this point, we're just going through a lot of these examples, and you guys have some practice examples that you can be working on. Regular octagon, oct meaning 8. Okay. So as we go through, six, 7, and back to our starting point. So one thing that we need to keep in mind is that we have to make it all the way back to the starting point, right? I don't want, if we're starting here, I don't want you to get to here and be like, oh, well, that's the last point because I started here, right? We need to make sure that we make it all the way around 360 total degrees of rotations. Rectangle. This is again one that it's four-sided, but it's not perfect shape, right? We've got 2 long sides and 2 short sides. So as we look, we've only got 2 rotations. Parallelogram has how many rotations? Go ahead and take a guess before we move on. You can pause the video. Okay. Now that we're back, let's take a look. Okay. So this is a parallelogram where 2 sides are long and 2 are short. Okay. A scalene triangle where none of the sides are the same, none of the interior angles are the same. How many rotations do you think it'll be? Pause the video while you hazard your guess, and then we will move on. Okay. We get 1. An isosceles trapezoid. Okay. 1. Remember, for rotational symmetry, we need to have images that can land on itself. If you've got like outlier parts, like this point that's sticking all the way out here, right? That will fit on except out there. And a kite. So here we go. A rhombus. This is a parallelogram where all the sides are the same length. A rhombus is defined by any four-sided shape where all of the side lengths are the same. We get 1, 2. So it's something to keep in mind, right? We've got the sides are the same, but we've got different interior angles. And so we have two sets of two angles. This one is acute, which means it's less than 90 degrees. This one is obtuse, which means it's greater than 90 degrees. And this angle here equals this angle. And this angle up here equals the angle down here. So as we're looking for rotation, right? Perfect shapes are important, but also interior angles. So we have two sets of congruent angles. So we end up with two rotations. With the isosceles triangle, right, where you had two sides that were the same, one side that was different, you had two interior angles that were congruent, but then you had this one guy by himself. So because you got that one angle by himself, we had one rotation we could make. We've got an ellipse here, so an oval, right? The interior angle clue doesn't help us out here because there's no interior angles on an oval or a circle. Hey guys, one last thing to be thinking about. If by any chance anyone ever asks you to calculate the rotational symmetry of a perfect circle, and a solid circle, no image on it, uh, run away. Okay, the circle is the one object in nature that if you try to find the rotational symmetry, it'll take you forever. It has an infinite number of rotations, so just keep that in mind as you move forward. Okay, hope this helps. Bye.